This is your presenter Asloob Mudassar, and I am presenting slide number 140 of the course on laser physics. Question is, describe the functionality and main features of a free electron laser system. We shall abbreviate the free electron laser system as FEL, F-E-L. The answer is, in a FEL, a relativistic beam of electrons is launched into a part of the laser cavity along the cavity axis, which passes through an undulator. Undulator is a periodic structure of a magnetic field where the moving electrons acquire wiggly motion in a plane orthogonal to the magnetic field. After passing through the undulator, the electron beam is deflected outside the laser cavity. During the passage through the undulator, the electrons are accelerated and longitudinal emission of synchrotron radiation is produced. The synchrotron radiations move back and forth between the cavity mirrors and interact with the relativistic electrons in the region of a magnetic field and produces a stimulated emission. So let me show you the structure of the FEL. Caption is schematic diagram of a free electron laser system. You can see that over here I have shown three directions. This is the beam direction, or you can say that on the arrow pointing towards the right, this arrow, which is the horizontal arrow pointing towards the right, is the Z direction. And the electrons are oscillating in this direction along this arrow. And you can assume that the tip of this arrow is the direction of y-axis. And the magnetic field is applied in this direction. You may take the upper arrow, that is this arrow, as the x direction. So we have x-axis over here, we have y-axis over here, and we have z-axis, positive z-axis over here. And you can see that the magnetic field is applied in the direction of this arrow, and the electrons are oscillating along the y direction, and the beam direction is the z direction, which is this one, and this is also the cavity axis, and the FEL beam is coming out from this end, and here this is a mirror, and you can see that these bold arrows actually are indicating the synchrotron radiation. These bold arrows indicate the synchrotron radiations. This is a 100% reflector mirror, whereas this is a partially reflecting mirror out of which the FEL beam will come out. And you see that here these are the magnets, periodic array of magnets, which we call as undulator. And at the bottom we have again the periodic array of magnets called undulator. The electron beam deflected out of the cavity. This arrow, you see that indicates that the electron is deflected out of the cavity, whereas the electrons will be oscillating along the y direction, that is perpendicular to the direction of the magnetic field and also perpendicular to the direction of the laser cavity, of the cavity axis. And here we can launch electron beam from the electron gun or the accelerator. So these are the electrons that we introduce into the laser cavity, either through the electron gun or through some accelerators. So this is the simplest diagram of the free electron laser system. Individual electrons oscillate transversely at an angular frequency omega q given by. Individual electrons oscillate transversely at an angular frequency omega q given by omega q is equal to kq times Vz is equal to kq times c, because we are taking the Vz to be nearly equal to c, nearly equal to velocity of light, and introducing the value of kq, which is 2 pi over lambda q into, and then multiplied by with c. So this is omega q, where lambda q is the period of the magnets. So you see that the magnets have been arranged periodically, that is from n, s, then again s, then again n, then again s, and so on. So these are the periodic arrangements, and the period, for one period we have lambda is the period of that, where lambda q is the period of the magnets, and Vz is nearly equal to c, is the velocity of the electrons along the z direction. The direction of the FEL output beam. So the direction of the z-axis is also the direction of the output beam from the FEL. High energy electron beams act as an amplifying medium in a FEL. So it means that the radiations which are produced in a FEL as an output beam will extract their energies from high energy electron beams. So these high energy electron beams actually provide a medium for the energy of the FEL beam. So the FEL beam energy will be proportional to the energy which is obtained from the high energy electron beam. Now consider a reference frame moving along the resonator axis with velocity Vz, to which the electrons in the undulator appear as oscillating electric dipole. The time t prime of an event measured in this reference frame, which is moving with the velocity Vz along the cavity axis or along the resonator axis, is contracted. So you see that since this is a moving frame, the measurement of time will be contracted, the measurement of an event will be contracted in this frame and can be written as given in equation number 1. So t prime, that is the time measured in this moving reference frame of an event, t prime is equal to square root of 1 minus Vz over c whole square, and then outside the square root sign we have time t, and this is the time which is measured in the frame of reference of the electrons, and this is the frame which is moving with velocity Vz. So this is the moving frame. So time measured in the moving frame is t prime, whereas the time measured in the electrons frame is t. And you see that if you said Vz is equal to 0, then t prime will be equal to t. In terms of the frequencies, if you want to write equation 1 in terms of the frequencies, you can take the reciprocal of this frequency, that is you have 1 over t prime, then equal to 1 over 1 minus square root of 1 minus Vz over c whole square, and then 1 over t, and multiplying by 2 pi on both sides, you can introduce the corresponding frequencies. So you can introduce on the left hand side omega prime, which is equal to 2 pi over t prime, and you can introduce over here omega q, which is equal to 2 pi over capital T, and then this term will be in the reciprocal. So we have omega prime is equal to omega q divided by the square root of 1 minus v z over c whole square, as shown in equation number 2, where omega prime is the frequency of the electron oscillations, frequency of the electron oscillations measured in the reference frame, which is of course moving with the velocity Vz. An observer in the laboratory frame, that is an observer in the stationary reference frame, will observe omega naught, that is electrons oscillatory frequency. Omega naught will be measured by an observer in the laboratory frame or in the stationary reference frame, which is equal to the frequency omega prime appears to have undergone a relativistic Doppler shift. So we can relate omega naught with omega prime, as if omega prime has undergone relativistic Doppler shift and is given by, as shown in equation number 3. So omega naught is equal to 1 plus Vz over C divided by the square root of 1 minus square of Vz over C, and then multiplied this whole term by omega prime. So we can introduce omega prime from equation number 2 over here, and then after cancellation of the common terms we can have omega naught to be approximately equal to 2 omega q divided by 1 minus square of Vz over C. This factor of 2 comes due to the fact that we are considering Vz to be nearly equal to C. So replace Vz with C, you will get C will be cancelled and you will get 1. So 1 plus 1 will be equal to 2. So here we are assuming that Vz is very close to C, and that is why we have written this relationship shown on the right hand side in equation number 3. So omega naught will be equal to 2 times of omega q divided by 1 minus the square of Vz over C. And you can write also equation number 3 in terms of the wavelengths. And you know that omega naught can be written as 2 pi into nu or 2 pi c over lambda. So omega naught can be written as 2 pi c over lambda naught, and this omega q can be written as 2 pi c over lambda q. So introducing these terms, replacing omega naught in terms of lambda naught and omega q in terms of lambda naught, equation number 3 is transformed into equation number 4, which is read as lambda naught is equal to lambda q over 2. And then we have terms in the bracket, which is 1 minus square of Vz over C. So equation number 3 gives you the frequency omega naught, the oscillations of the electron frequency in the laboratory frame, and lambda naught is the wavelength in the laboratory frame. As Vz is close to C, lambda naught is much smaller than lambda q. Consider the relationship. 1 minus square of Vz over C is equal to square of m naught C square over E. This is a very common equation, because if you arrange this equation in such a way that you solve this equation for E, that is E is on the left hand side and all the terms on the right hand side, then this equation will be read as capital E on the left hand side will be equal to m naught C square divided by square root of 1 minus Vz, 1 minus square of Vz over C. And in that form you will recognize this equation very easily. So this is the energy, capital E is the energy of the electron related with its rest mass energy. So equation number 5, which is valid for a free electron moving with velocity Vz and having the total energy equal to E. The electron is undergoing, if the electron is undergoing wiggly motion, the relationship given in equation number 5 can be expressed as. So you see that for a wiggly motion, we can introduce a factor 1 plus k square on the right hand side of equation number 5. So we have introduced 1 plus k square, a factor on the right hand side of equation number 5 to write down the equation number 6. Where capital K in equation number 6 is the undulator constant capital K and is given by capital K is equal to E times the square root of average value of a B square multiplied by lambda q divided by 2 pi m naught C. This is a dimensionless constant, where B is the magnetic field of the undulator and its value is average along the z direction. Thus, equation number 3 and equation number 4, that is these two equations, equation number 3 and equation number 4, can now be written as, in the presence of the undulator constant capital K, for the wiggly motion of the electrons, we can write this relationship shown in equation number 8, which is omega naught is equal to 4 pi c over lambda q, and then we have 1 over 1 plus k square, and then we have E over m naught c square, the square of this whole quantity. And similarly, for equation number 4 can be written as lambda naught is equal to lambda q over 2 and then 1 plus k square, and then we have m naught, the square of m naught c square divided by e. So what we have done is that we have replaced this factor, which is 1 minus vz square of 1 minus vz over c in equation number 3 and equation number 4. This factor, that is 1 minus square of vz over c, and in equation number 4 the same factor 1 minus vz, 1 minus square of vz over c have been replaced using equation number 6. And then we have written those equations, that is equation number 3 and equation number 4 have been transformed as equation number 8 and equation number 9 respectively. In a given FEL system, if lambda q is unchanged, then electron energy capital E can be used to obtain the desired range of lambda naught. So we can obtain desired range of lambda naught provided lambda q is constant in a given FEL system. For typical FEL system, if lambda q is of the order of 10 centimeter and undulator constant capital K is of the order of 1 and E, then the energy E varies from 10 to the power 2 to 10 to the power 3 million electron volt, which is the energy of the electrons. If you introduce electrons in the cavity with in the laser resonator with this much energies, then the lambda naught will vary from infrared to UV. The electron emission as observed in the reference frame lasts for a time. So the electron emission lasts for a time delta t prime, which is related through this relationship. So this is the same relationship that we have written before in terms of t prime is equal to a square root of 1 minus square of vz over c, and then outside that one we have capital T. This relationship we are again using, but in terms of delta t prime and delta t. So the electron emission as observed in the reference frame lasts for a time delta t prime, which is equal to the square root of 1 minus the square of vz over c multiplied by delta t. Where L, here we are introducing delta t in terms of L over c. Where L, where L is the length of the undulator and c is the velocity of light. So you can find delta t over here. A radiating electron in this time interval will emit a number of cycles, and the number of cycles that will be emitted by the electrons in this interval will be given by n cycle, that is the number of cycles is equal to omega prime over 2 pi multiplied by delta t prime. So omega prime is the number of cycles per radian, so you are dividing it by 2 pi, that becomes number of cycles per second, and multiplied by the time you will have this as number of cycles. So this has the dimensions of number of cycles. That's why we have labeled it with n cycle. So number of cycles are given by omega prime over 2 pi multiplied by delta t prime, and the delta prime has been defined over here with the delta t given by L over C. But you know that the number of cycles can also be found from this relationship, that is the length of the undulator L divided by the wavelength there, which is lambda q, which is the periodic arrangement of the magnets. And lambda q, you know that I have also defined earlier, which is the spatial distance between the periodic arrangement of the magnets. So we have the total separation, the total length of the magnets in the undulator is L divided by lambda q. So the number of cycles is also given by L over lambda q. So a radiating electron in this time interval will emit a number of cycles, n cycles, of equal magnitudes and equal periodic and equal period, forming a square pulse. So you see that these are the cycles of the electrons, and these cycles have the same magnitude and they have the same period. So with the same magnitude and same period, these collected cycles will actually result in the form of a square pulse. A square pulse containing n cycles of equal magnitude and equal period, so forming a square pulse. Let us rename n cycle as n omega, where n omega is equal to L over lambda q. So you see that we have the square pulse. If you take the Fourier transform of the square pulse, you will get a sinc function. And you know that the sinc function is defined by, for example, sinc of x will be equal to sine of pi x divided by pi x. So this is the definition of the sinc function. If you want to see the details of the sinc function, you can consult some of my slides on Fourier optics course. So you have a square pulse, and if you take the Fourier transform of the square pulse, you will get the sinc function. And the sinc function is nothing but the sine. For example, sinc of x will be equal to sine of pi x over pi x. And if you take the square of that sinc function, you will actually get the power spectrum of the square pulse. So the power spectrum of the square pulse is of the form power spectrum denoted by y is equal to the square of this is actually a sinc function, that is a sine of x divided by 2 over x divided by 2. Because I have not written pi over here, because the pi is introduced in the definition of x. You see that, you can see pi over here. So this is the power spectrum of the square pulse, where this x is actually 2 pi times n omega and multiplied by nu minus nu naught divided by nu naught, where nu naught is the central frequency of the gain profile of the radiations emitted in the beam. So we can say that x is equal to 2 pi times n omega times nu minus nu naught divided by nu naught, where nu is any frequency on the gain profile and nu naught is the central frequency of the gain profile. And you can introduce delta nu naught as the spectral width at full wave half maximum of the gain profile, which can approximately be written as delta nu naught is equal to nu naught divided by 2 times n omega. The plot of y versus the dimensionless quantity x is shown in part number A of the figure 2. That is this one. The caption of the figure is plot of the power spectrum density y versus x in part A. So here you see that in the part A you are plotting the power spectrum. And you see that this is the power spectrum, which is actually the square of the sinc function. And you know that the main lobe in the center has the maximum value, and on both sides it has a symmetric form and decays to the minimum value. And then you see that after I have shown only one side lobe over here, and if you take a further extension of the values of x, you can have other side lobes, but with the diminishing values nearly zero. So only the first side lobe is important. This is the main lobe of the spectrum, of the power spectrum, and this is this one, and this one is the first side lobe. And you can see that in the main lobe, the power spectrum indicates that the main frequency will lie in this region. The other frequencies are also present. So a full range of frequencies in the range of x going from -5 to +5, these all frequencies are present in the spectrum. And then the spectrum becomes zero at some point, and after that you can also have some other values in the spectrum, other frequencies, but these have diminishing or very small values, and we can ignore them. So all the frequencies which are lying in the main lobe or in the central lobe are important. So this is the power spectrum, which means that all these frequencies are emitted in this region, are available for the FEL system. So let me read this paragraph again, where x is equal to 2 pi n omega times nu minus nu naught divided by nu naught. The spectral width delta nu naught at full width half maximum has the following approximate results. That is, delta nu naught is equal to nu naught divided by 2 times n omega. The plot of y versus the dimensionless quantity x is shown in part A of figure 2, which I have just shown you and explained. This line shape is the same for all other electrons if they travel with the same velocity, and is regarded as the homogeneous line shape of the FEL laser. So this is only the case when we are talking about the homogeneous line shape, that is, all the electrons have the same energy. Then under that condition we have the power spectrum, which we have shown over here. An inhomogeneous line shape can be observed if either the electrons are non-monoenergetic or have angular divergence, or the magnetic field varies over the electron beam cross section. So under any one of these three conditions, we can have inhomogeneous line shape. In the rest frame of the electron, the otherwise static magnetic field will appear to the electron like a counter-propagating electromagnetic wave, and the emission of the synchrotron radiation may be considered as the Compton backscattering of this viral electromagnetic wave, and is referred to as the Compton FEL, that is the Compton free electron laser. Here in this diagram, you can see that the electron is oscillating. That is, the electron is not moving in a rectilinear path, but is moving in a curved path and changing its direction. So due to that one, when the electron is moving in a curved path, in a very strong magnetic field, then of course the synchrotron radiations are emitted perpendicular to the direction of the electron oscillations. That is along this axis. That is along the axis of the radiator, along the axis of the laser beam, on the axis of the beam. So you see that I have also shown here the direction of the synchrotron radiations, which are produced when an energetic electron is moving in is forced to move in a curved path due to the strong applied magnetic field. And the electrons and the synchrotron radiations are generated, which are perpendicular to the motion of the electrons. An inhomogeneous line shape can be observed if either the electron are non-monoenergetic or have angular divergence, or the magnetic field varies over the electron beam cross section. In the rest frame of the electron, the otherwise static magnetic field will appear to the electron like a counter-propagating electromagnetic wave, and the emission of synchrotron radiation may be considered as the Compton backscattering of this virtual electromagnetic wave, and is referred to as the Compton FEL. The FEL stimulated emission cross section. The FEL stimulated emission cross section is associated with the backscattering of light. The spectral distribution of cross section shows gain for low frequencies and loss for high frequencies, as shown in part B of figure number 2. Consider this last sentence again. The spectral distribution of cross section shows gain for low frequencies and loss for high frequencies, as shown in part B. This one. And the corresponding caption is The stimulated FEL stimulated emission cross section in part B plotted versus the X values. So you can see that is along the vertical axis we have the stimulated emission cross section plotted along the vertical axis and X along the horizontal axis. You can see from on either side of this zero reference point, for example on this side, on the left hand side, we have the low frequencies close to that one, and for that one the gain increases for the low frequencies and up to the value of a -5, then you see that for higher frequencies the gain falls to 0. And similarly on the right hand side the gain is increasing negatively for the linear frequencies, and after that one beyond the value of 5 the gain you see that will decrease negatively. So for the low frequencies the gain is high for the low frequencies, but for the high frequencies it has the lower values. This is what has been stated in the last sentence, that is the spectral distribution of cross section shows gain for low frequencies and loss for high frequencies, as shown in part number B of figure number 2, which was this one. First FEL was demonstrated at Stanford University at lambda is equal to 3.4 micron. The E-beam consisted of pulses of length 3.2 picosecond with the separation of pulses equal to 84.7 nanosecond, and with the cavity length capital L is equal to half c into tau is equal to 12.7 meter. The FEL was operated in synchronous mode locked regime. FEL efficiencies are very low. The emitted frequencies draw their energies from the electron in the beam. So this sentence is needs to be remembered, that the emitted frequencies draw their energies from the electrons in the beam. The maximum extractable energy is the energy that shifts the operating frequencies outside the gain profile. So for those frequencies which lie outside the gain profile, for that one the energy will be maximum. So the maximum expected energy is the energy that shifts the operating frequency outside the gain profile. The efficiency of FL is the ratio of this maximum energy to the initial electron energy and is roughly given by eta. So eta maximum is approximately equal to delta nu naught over nu naught is equal to 1 over 2 times n omega. Typical values of n eta are in the range of 10 to the power minus 2 to 10 to the power minus 3. Tapered Wiggler, where lambda q over e square is kept constant by gradually decreasing lambda q along the path of the electron beam, has been implemented for increased efficiency. So you see that this factor, that is lambda q over e square, has been kept constant by gradually decreasing lambda q along the path of the electron beam, has been implemented for increased efficiency. Before the electrons leave the Wiggler, the remaining energy is extracted by decelerating them to increase FEL efficiency. In Compton FEL region, where energy of the electrons in the beam is greater than 10 million electron volt, but at low currents of the order of 1 to 100 ampere for electron beam. So you see that for the Compton FEL, the energies of the electrons should be in greater than 10 million electron volt, but with the reduced currents in the range from 1 to 100 ampere for the electron beam. In Raman FEL regime, low energies, for example, E in the range from 1 to 2 million electron volt for the energies of the electron and have with the currents with the high currents in the range from 10 to 20 kiloampere are used for the electron beams. And this factor is important for the Raman-FEL region. In this case, the FEL operates in the millimeter wave region. So you can notice that this millimeter wave region, which is an important part of the spectrum obtained from the Raman-FEL region with these parameters, that is the energy should be in the range of 1 to 2 million electron volts with the currents in the range of 10 to 20 kiloamperes. FEL has very good wavelength tunability. FEL can operate in wavelength regions where other lasers cannot operate due to the absorption of light by the physical presence of the laser medium. So you see that this sentence explains that why FEL are important and what is the difference between FEL and other systems. So let me read this sentence again, and you concentrate. It will be obvious that why FELs are important. So FEL can operate in the wavelength regions where other lasers cannot operate due to the absorption of light by the physical presence of the laser medium. And you know that there is no physical presence of the laser medium is there in the FEL system. Since no laser medium is present in a FEL, thermal effects cannot limit the optical power. FEL can also be operated in pulses. FEL can provide a powerful infrared source which finds applications in material processing, for example, nano and biotechnology. So you see that here I have briefly introduced the FEL system. The further detail is beyond the scope of my present lectures, but this will be enough to give you an idea what are the FEL systems, and some basic equations have been given and some basic information about the FEL system has been disclosed in this lecture. So this is the end of slide number 140.